I am Saeed, and I'm going to discuss two projects that I've been working on this kind of semester as part of the Vector Institute and Large Language Modeling group. So I'm going to describe kind of two techniques for discrete prompt optimization in the setting of kind of parameter-free prompt optimization. So as a simple introduction to prompting, we have very powerful pre-trained language models, and they can generate any text. And we want to guide this language model to generate our a desired output in a downstream task. For example, here we have on the left a sentence classification task where we have a review as an input, and in the output we want basically the model or the language model to generate its sentiment. So with prompting, what we do is we include some instructions, and as you see in red here, we have an instruction, and we hope the model will use this instruction to properly generate the output that we want. In kind of our the project itself and the experiments that I've done, so we need to choose one language model to kind of experiment ideas on. And I worked with T5 large language model, which is a encoder, decoder, sequence-to-sequence model with multiple layers of kind of transformer layers. And one thing which is interesting is that if we want to kind of fine-tune weights in this T5 model, we have to adjust around 770 million parameters. But kind of with two techniques that I worked on this semester, we update 0 parameters. So it's a parameter-free prompt optimization technique. And we don't update any parameters in the model, but we also don't introduce any parameters. So it's possible that some techniques, they may generate prompts using another model, but that model also has some parameters. But these two techniques that I will describe, they're completely kind of parameter-free. So when I'm talking about discrete prompt optimization, the goal is to basically search in the vocabulary space of the prompt sequence to find an alternative prompt, but it is scoring higher compared to your initial prompt. So here we have an example on the right that this is our initial prompt, and actually after optimizing it with one of the methods, we can end up in this ungrammatical prompt, but actually performing better compared to the original one. So with discrete prompt optimization, the optimized prompts may not be grammatical or sensical, but that's something reported mostly in the research papers. The two techniques that I kind of implemented, one was gradient search-based prompt optimization based on a technique called autoprompt. And then the second one is GRIPS, or gradient-free edit-based instruction search method. There is a difference between these two techniques, which I'll just describe in the next two slides. But one of the methods, gradient search, it actually requires kind of storing gradients in the model. But the second one, GRIPS, is also gradient-free. So both are parameter-free. The first one does require gradients, but the second one is also gradient-free. This is this distinction is important because let's say you want to use an API from ChatGPT or any other big tech company providing these large language models. So we don't have access to activations of the model itself, or we cannot even kind of ask that API to provide gradients or kind of the backpropagation results with respect to its weights. So the only alternative that we have is the second method, GRIPS, which is gradient-free. So to briefly mention what gradient search is doing, so we have a training data set, and in each iteration, we're like selecting one mini batch of training examples. We have a print-based template, and at random, we pick one of its tokens. We call this token PI. Then we compute the gradient of the likelihood of the language model with respect to the embedding vector for that particular token PI. So we know that these tokens are being converted into feature vectors. So now we compute the log likelihood with respect to that feature vector. And basically, we're going to move in the direction of this gradient vector, which increases the likelihood. But this direction is something that we want to discretely search. And kind of the search directions are given by the new alternative tokens from our vocabulary. So basically, we're looking for an alternative token that can be replaced instead of PI, and that can help to kind of increase the log likelihood. But we kind of approximate that increase with this like a first order approximation to the change in the log likelihood. So we cannot analyze every token. Therefore, in the algorithm, there's a hyperparameter K, and we choose, for example, let's say top 10 tokens. And those top 10 new tokens now end up in new 10 candidate prompts. And now we can form the new candidate prompts and reevaluate them again on the same mini batch, or actually in another mini batch from the training data. And then we pick the best one and continue search. We go to, again, step one. And this is just the training loop. In the implementations, we also have a held out like validation split. And we constantly check the performance on that held out validation data. And if the prompts are basically are doing good, then we store it. If not, we reload the previous based prompt. In the second method, GRIPS, is kind of similar. So again, we have a mini batch from the training data set. This algorithm can actually happen at 4 levels. So whether we want to search in the word level, or we actually want to search in phrase level, or if you have a document that you want to see if you make changes in the sentence level, what would be the performance. But in the experiments, we chose the word level kind of search. Basically, what you do, you have 4 edit operations to perform on the, let's say, tokens of your input. The first one is delete, where you randomly delete one of the tokens, or you add one of the previously deleted tokens to randomly somewhere in your prompt, or you swap it with another randomly token in the input, or you actually use another model like a paraphraser that paraphrases your, like, let's say, phrase, and you now replace the phrase with like its paraphrase in the prompt. So basically, you make these candidate prompt templates by performing these like random edits on your prompt, and then you evaluate those on the according to your mini batch. But here, the evaluation or your score function doesn't depend on the log likelihood or its gradient. It's actually the task performance or some variant of the task performance. So, for example, we're interested in accuracy for this like classification task, sentence classification. So we basically compute the accuracy or even some alternatives by including like the entropy of the predictions. And basically, we again store the best prompt and we move to the next loop of the algorithm. As you see, the main difference, I would say, is that the score function in the GRIPS is the task metric, but in the previous one, it's actually it depends on the gradient, which is really hard to compute in like big language models. So we have some kind of notebooks, and the experiments that we did with these 2 techniques on 2 different sentiment classification tasks. We have semi-val with 3-way sentiment classification, basically classify inputs into positive, neutral, or negative. and the binary sentiment classification task classifying inputs into positive and negative. And we see that both methods are improving a lot, at least on SST2 dataset. They are improving significantly, and Greeks is slightly performing better than gradient search. And these results are kind of interesting because, again, we don't introduce any parameters. It's just a parameter-free search method. One difference between these two techniques, which is interesting and also helpful for experiments, is that since gradient search requires kind of computing gradients, you need more memory to store the states of the parameters during backpropagation. So you end up using a smaller batch size compared to CRIPS, where you can use larger batch size because you just evaluate the kind of your method on a data set. So it's more like inference than like training step. And also I have some examples showing you the optimized prompts with these techniques. So this is the example for gradient search. We have an initial prompt, like a grammatical thing, like generate the sentiment of the next sentence, and then this becomes this like nonsensical prompt. But successfully, the search could find the labels like negative, positive, and kind of included those labels in the input, which is interesting. So in the second example, we have a longer instruction for the Greeks method. So we say, like, in this task, you're given sentences from movie reviews. The task is to classify a sentence as positive if the sentiment of the sentence is great, or as negative if the sentiment of the sentence is terrible. The optimized prompt is, we cannot read it, but as we see, there are some perturbations in the input, like we don't have the token task, it's being removed, or we have some dots added into the input. But overall, back to the table, that like perturbations, they contribute a large, like a significant increase in the performance. So kind of, this is my final slide. We have, as part of the prompt engineering lab, we have these notebooks to try, and also the main repo with more other experiments about prompt engineering. And thank you.
Hi, Saeed. Great presentation, very interesting. I have to admit that I don't have a very strong background in large language models, but this is definitely a very interesting area. So my question is, through this research, how do you see it being applied to like businesses that are doing something with prompt engineering? Is it that you're using this algorithm to transform whatever someone types in natural language into the more optimized prompt, like in the background, so that it comes up with a better search result? Is that sort of the idea of the research?
So with prompt optimization, yeah, the goal is to just to get a final, like a better final performance on the task that business is interested. But that comes with the loss of interpretability because these prompts are not grammatical. So I guess the goal is to just get a better performance without actually updating the model, or without kind of the cost of updating all the weights of the model.
So then the actual person that types in the prompt, they'll use natural language, but then they won't see the optimized prompt, but that's what's going to happen underneath, and it'll give them a better result?
I think that can happen, that in the background, or that like the API provider can optimize the initial prompt of the user. But right now, I see that these prompts are being optimized per task and not like per user. So it's like if you're doing this task, and like there's out of all the possible prompts, there's this one that performs the best according to like a validation data. So it's more like a task-based query than like a person-based query.
Okay, thank you so much.